maybe people are just realizing that they're just can watch all your lectures.
Yeah. Okay, differential first law, number 4.
Yes.
Joe forgot his.
Yes.
Looks much less unappealing than it normally does.
Let's see.
Did you know you don't have to save it? You can just paste it right in.
Actually, I always save it and then paste it in, so it's the deluxe model. Okay. So we got this refrigerant, and we have a pressure. And specific internal energy contained in a closed tank. Okay, so we know we're going to use the form, so d kinetic energy dt plus d potential dt plus the internal energy dt is equal to q dot minus w dot. And we know that energy is being transferred to the refrigerant. Our system is the refrigerant at this rate. So W dot, remember W is positive if the system is doing work on the surroundings. So this is going to be negative 0.1 times 10 to the third watts. And that pressure sure seems like it's not going to do anything. Our starting internal energy is this times the mass of 1 kilogram. So
when it's kilojoules. And I think that might be what tripped me out.
Okay. 232.92 times 10 to the third joules. And it's in a closed tank, which means there's no change in volume. So there's
so that dV/dt is 0.
That's a different V.
Oh,
yeah, this is potential, but I think it looks like I don't see any reason to think that these are going to change. So we're, the kinetic energy and potential energy, you're just going to neglect those anytime it doesn't say anything about a speed change or a height change, right? So the change in volume is 0, which means there's no work of expansion. And heat transfer occurs. Okay, so now it's from the refrigerant. So this is equal to so Q dot is going to be negative KT, where that's in minutes. So we want, so if we want to change it to seconds, let's make this negative KT over 60.
Would it be negative 1,000? That's in kilowatts?
Oh, yeah, you're right. So 1,000 over 60 is,
50 over 3.
okay, so 16.6, I think. 16.6 repeating KT in seconds. Okay, and so du dt is equal to negative 16.6 times kt minus negative 0.1 times 10 to the third. And what are we trying to find here?
K. Right. Oh, so yeah, so then you have to, right, integrate it to find U and then solve for K.
But we only have a starting specific internal energy. So that's just going to give us our, okay, so.
Oh, don't we have 2? I wrote down 2 in the, where did I get that other number? I wrote down U2 equals 276.
Oh, really?
I must have, I wonder if I just pulled that from a different problem.
Or maybe that was in the solution?
Maybe.
Okay, so yeah, so we can definitely write this as negative 16.6 kT plus, that's 100 dt. And that says that the change in U is equal to negative 16.6 kT squared over 2. So this is 8.3 repeating. And this is plus 100K
Would it make
plus
sense
C.
to call it also, or like U of T, or instead of delta U? Is that?
Well, it's not, if you integrate, if you just integrate like an increment, an infinitesimal increment, it gives you the change.
Okay.
And so you can write it like this, and then that change is, U2 minus U1.
Okay.
And this is equal to, and so this C is your U1. So that cancels with, oh no, that's plus U1. So let's see, this is, like, think of we're doing this from instant 1 to instant 2. And this is from instant 1 to instant 2. And so that's the change in U. And this is the later time minus okay, think of it like this. This is U2 minus U1. And this is, we'll just call it from time 0 to time 2. So, or from time 0 to t. And so this is negative 8.3 repeating kt squared plus 100t. So I'm going to get this out of here. This is a clear way to think of it for this problem. And then we know what that U1 is. So U2 is just equal to negative 8.3 repeating KT squared plus 100T plus our starting, our U1 is 232.92 times 10 to the third. And now if we had a U2, we could solve for K.
Which I think in the online problem, I think we do.
Okay.
Is that?
Oh, number 4, I skipped a whole bunch of stuff. We have more information.
Yeah.
Okay. So yeah, we know U2. No change in. Okay, so we already got Q and W. And then you can.
Yeah, so then you would just solve for K. And so the pressures
Right.
are meaningless in this one.
They are meaningless. A lot of the books that I take from the book and stuff have just sort of red herring. Yeah.
Okay.
But so now, right, 270. So now 276 point 67 times 10 to the third is equal to all this stuff where T is equal to 20 minutes worth of seconds. We've changed everything to seconds. So that's 20 times 60. So 1200, right? I think so. So negative 8.3 K times 1200 squared plus 100 times 1200 plus 232.92 times 10 to the third. And then you can solve for that K.
Yeah. Okay. Thank you.
Any questions about that one? Okay, so if you so you can always think of, so if you are integrating some variable, some random variable, I'll give it a name, M or something, this is any variable. You can integrate it thinking of it at some initial instant and some later instant. Okay, and then what you have is M evaluated at instant 2 minus that M evaluated at instant 1.
So does it make sense to, like, for the most part, just to say from 0 to T?
Well, so the different variables have different, the instants have to match up, but the variables are different. So, but yes, you can think of it as, time equals 0 or whatever.
Oh, so you're saying you could integrate two different sides with two different variables as long as they're at the same.
As long as they represent the same instant, the same state,
Sure.
Yeah.
Yes, calculus is crazy.
So, yeah.
No, that makes sense. Thank you.
Okay. Does that make sense to anyone else? Do you have any idea what I'm talking about? So that's actually gonna come up quite a bit in this class, where we're gonna integrate and to get that change in variable values, and we're gonna think about just doing our integration from some starting instant to some ending instant. I'll try to point it out as it keeps coming up. Okay, so last time we started talking about simple compressible substances, and so today I want to introduce the tables and talk about linear interpolation. And so the key thing for the tables is the tables only give finite numbers of values, right? It's not a continuous like function of values. So in general, after we get through this section, a lot of the times when I give problems where you have to look stuff up in tables, I'm going to give you, the values that you're going to want just happen, to be values that are there in the table, so you don't have to waste a lot of time doing this. But in general, if you're looking for a random value, that value is not going to be given in the table.
So
And
it's
so-
just kind of too chaotic to give it any sort of useful function, like to fit over it.
No, people do fit functions over it, and but it's complicated to use. But yes, I mean,
Big polynomials or something.
yes, they're big polynomials. I mean, really, people don't even use. I mean, there's just people who do this for a company or whatever just have function values where they just enter the thing in and they don't even have to know what the function is. They just put their thing into a calculator and it spits it out. But I think this linear interpolation is important enough for engineering generally that I think it's worth spending a little time understanding how it works. I mean, so much of engineering approximation is based on this. Okay, so in general, you need to interpolate between two given values to estimate the desired value. Okay, and we're going to always think of interpolation so we're going to think of interpolating a function f of x, and x is the value you know at the desired state. F is the value you want at the desired state. Okay, so let's look at what these property tables look like. These are all given in D2L. So this is so remember we have saturation tables where you just look things up by a single index value. Those are the easier ones to use. And then we have the tables that aren't saturation, like compressed liquid or superheated vapor, where we have to look it up by two indexes, and that's more of a pain, So this is what a saturated table looks like. This is for water. And remember, the saturation states are when we're in that boiling transition. Okay, so a saturated liquid, if you add more internal energy to a saturated liquid, it starts to become a vapor. A saturated vapor is if you remove internal energy from it, it starts to go from a vapor back to a liquid. Okay, and here's what the properties table looks like. So we have two of these saturated water tables. We have one that's indexed by temperature, that's this one. Okay, and so the idea is if you know that this thing is at its boiling point, if this water is at its boiling point, then for a given temperature, it has to be at this corresponding pressure. Otherwise, it wouldn't be at the boiling point. Okay. So let's find atmospheric pressure roughly. And what do you expect? So,
100?
well, right. So for the pressure to be at 1 atmosphere of pressure, we expect the temperature to be 100 degrees Celsius, right? Because that's the boiling point at atmospheric pressure. And so we'll go down to 100. And what we see is in bar, that's 1.01. So that's 1.01 times 10 to the 5th pascals. Okay. So the only pressure where saturation occurs at 100 degrees Celsius is atmospheric pressure. And if the pressure gets lower, it takes less to boil. It takes less temperature to boil. For like mountain climbers who are living at very low pressures compared to atmospheric pressure, there gets to be a major problem with cooking your food because your water boils at too low a temperature to cook the food very well, you know? And so it's hard for them to make ramen or rice or whatever. It takes forever because they're trying to do it with water that's at 70 degrees, you know, or whatever. And now notice so here are the variables that occur in these tables. Specific volume, so that tells you how dense it is. Internal energy, and that's a specific internal energy. Enthalpy and entropy, which we haven't talked about yet, but we will. And notice that in each one of these, there's 2 columns, okay? So we're talking about water, but you have different values depending on whether you're looking for a saturated liquid or a saturated vapor. Okay. Specific volume, think of this specific volume. So imagine water at atmospheric pressure at the boiling point. Specific volume is how much volume you have per kilogram of water. So do you expect a bigger volume to be taken up by a kilogram of water when it's a saturated liquid or a saturated vapor?
Vapor.
Yeah, so the vapor is more spread out, so a kilogram of it takes a big space, you know? And so look at these values. This is saying, this is a little confusing, but it's saying here, can you guys see this? Mm-hmm. It's saying it's the specific volume times 1,000 is what they're giving us, which means that whatever values they give us, you need to multiply by 10 to the minus 3 to get the actual value. You see what I mean? It's confusing. But so what this is saying is at boiling and atmospheric pressure, the volume taken up by a kilogram of liquid water is 1 times 10 to the minus 3 cubic meters. The volume taken up by a kilogram of steam at the boiling point is a little over 1,000 times as much volume.
That's basically like a liter, right?
A liter?
Is that like 1,000th of a cubic meter?
A thousandth of a
or a
cubic
milliliter?
meter? I don't remember the relationship between those.
Well, because right, isn't like a kilogram of water a liter?
Let's see, a gram of water is 1 cubic centimeter, I think.
It doesn't matter.
Yeah. But anyways, I'm just trying to get you like oriented on like what stuff is here. And so if you're at atmospheric pressure at the boiling point and you want to get the specific internal energy of liquid saturated water, you go across here and look at the liquid one. And so 418.94 times 10 to the third, if you want to get it in SI units, joules per kilogram. And then you can see the giant increase in energy if you're talking about a saturated vapor. You remember I mentioned latent heat last time? Latent heat is the heat that is in a boiled substance, a vapor substance that doesn't show up in the temperature. And so this is a measure of the specific latent heat right here. This minus this, that's the amount of energy, because these two are the same substance at the same pressure and temperature, okay? And so the difference in those energies is the amount of energy that's available to be used for engineering purposes without any change in the temperature.
So like in an air conditioning system,
Mm-hmm.
the vapor that goes outside, right, to carry the heat out of the, like,
So the
like it would come in as a liquid and then go out as a vapor, the refrigerant. Is that, am I thinking about that right? Because you want to store all the latent heat in it.
So it goes, so in a refrigeration system, you want the temperature to get very high. As it goes into the coils in the back of the refrigerator or whatever, you want the temperature to get very high, so you compress the gas. It condenses into a liquid at a high temperature.
Okay.
And then it goes through, lets out the energy, comes through, it's allowed to expand, which turns it into a gas.
So then no, what I said is wrong.
I guess it's backwards.
Yeah.
Yeah.
Thank you.
Okay, so that is a saturation table. And then there's also here saturation table for water indexed by pressure. It's the same thing. It's just that you look it up in terms of the pressure instead of the temperature. But again, if we go to pressure now, that's at atmospheric pressure. That would be so that would be 1 bar about. We expect the corresponding temperature to be 100 degrees Celsius, and you see it there. Okay, but everything else is the same. You have the saturated liquid column and the saturated vapor column. Okay, now what's going to be different when we go to the compressed liquid and superheated vapor tables? So let's go to, here's water, the compressed liquid table. Now you have to look things up by 2 variables. So how do you do that? Well, they have it separated up into smaller sections. It's basically an individual table at each pressure. Okay, and under each pressure, it's indexed by temperature. And obviously it's a much smaller table because you don't have, it takes up a lot of space. But so if you have something if your vapor, oh, this is a liquid. If your liquid is at 50 bar for a pressure, you'd go to the table that's 50 bar, and then you'd go down here to the temperature, whatever temperature you want, 200 degrees Celsius, and these are the values. Okay. It's a lot less tedious if you're at saturation. But the lucky thing for us is for a lot of our purposes, we're going to be at saturation, you know. Anybody have any questions about the formats of those tables? We have these for water, a specific refrigerant that's popular or was popular. Ammonia. And then we'll talk about the ideal gas tables later. Okay, so now let's say that, let's go back to this for a second. Let me just go back to the saturation table for water. And let's say that we do a calculation, and what we need to know is the specific internal energy for liquid water at saturation at 25.26 degrees Celsius. And we need that precision, okay? Well, obviously, a table can't present continuous values. So how are we going to use the specific internal energy at 25 degrees Celsius and the specific internal energy at 26 degrees Celsius to give us an estimate of the specific internal energy at 25.26 or whatever I said? Okay, so that's what our goal is. And we're going to use linear interpolation for that. So for values of properties between the given values, the given table values, we're going to use linear interpolation. And I'm going to show you how this works with mathematical functions. But remember that what I'm showing you with mathematical functions is also the way we're going to do it with the tables. If you just think of the x value of the function, the independent variable of the function, as the value we know, and the f value as the one we have the bounding values of and we're trying to approximate. Okay, so linear interpolation. First we'll just think of it in terms of a function f of x. And say that our function looks like this. And we know these two values here and here. And we want to approximate the value here. Okay, so I'm going to call this x1. This is x2. Okay, we know f of x1, that's given in the table. And we know f of x2, that's given in the table. So we know both of these. And we want to approximate this. And so the way we're going to do that is we're going to assume that this function is linear between these two values. And this is going to be our approximated value. Obviously, the function I chose, like that's a pretty bad approximation, it looks like. But that's the idea that we're going to use. And so to approximate this, so this is, I'm going to call this value x, okay? That's where we want to approximate this function. So this x is the value we know. Okay, we know we want to be at x equals 2.69 or whatever, you know. And we want to approximate f of 2.69. And so the function, which is just an equation that gives us the value lying on this line, says f of x is about equal to f at x1 plus the slope of the line between these two function values. So that's going to be the rise over the run multiplied by x minus x1. So this is the function we're always going to use. Anyone have any questions about the idea? Or so it's a little bit of a messy looking equation, but I think it's probably worth, instead of just trying to memorize it, think about the meaning of it. You know, it says you start at this value. Okay, so we're going to start here, and then we're going to define the slope of the line here, and we're going to travel as far along that slope as we need to be this far along the line. So we're going to start with the function value at x1, then we're going to take the slope of the line and travel along it x minus x1. Okay, let's see it work with just a mathematical function. So we want to approximate f of x is equal to x squared at x equals 2. And we're doing that given that f at 1.5 is equal to 2.25, and f of 2.5 is equal to 6.25. So if this was a table, so if these were table values, we would know we want the value of the property f where the property x is 2, okay? But the table only has the property f at x equals 2.25, no, 1.5, and x equals 2.5. Okay, and so the fact that we know this function, we won't have that when we use tables, but here it's just a way to see how close our approximation is to the actual value. Okay. So f of x is equal to f at x1, which is 2.25. Okay. Plus, now we have the slope. So that's going to be f at 2.5 minus f at 1.5. So that's 6.25 minus 2.25 divided by the change in the x value divided by x2 minus x1. So that's going to be 2.5 minus 1.5. So that's the slope of the line. And then we're going to multiply it by the x value we want minus x1. Any questions about that yet? Now you just plug those values in, calculate it, and it gets, I should probably change that to an approximate equal sign, that f is about equal to 2.25 plus 4 times 0.5, so that's 4.25. Since we're doing this with a mathematical function where we actually have access to the true value, you can see that the true value should be 4. We got 4.25 as an approximation, which is quite a bit better an approximation than either of those two endpoint values, 2.25 or 6.25. So you can see the benefit of doing this linear approximation rather than just choosing the closest value you have, Okay, this is a 1D interpolation. And you can always use this approach for values in the saturation property tables. Okay, so let's just do we have 5 minutes. Let's just do a quick example using actual saturation values, okay, instead of a mathematical function. So we're going to use, for saturated water vapor, we want to know at a temperature of 63 degrees Celsius, what's the specific internal energy? Okay, so we're talking about saturated water vapor, so don't make the mistake of using the saturated liquid water column, And we're just going to go to this table. 63 is what we want. So I'll go down here to see how close the temperature gets to 63, and we have a 60 and a 65. Okay, so that's going to define our two boundaries. So for saturated water vapor at 60 degrees Celsius, we have a specific internal energy of, skip over the saturated liquid, and we have 2456.6. That's kilojoules per kilogram. So 2456.6 times 10 to the third joules per kilogram. And then at 65 degrees Celsius, we have 2463.1. Times 10 to the third joules per kilogram. And I'll call these U1 and U2. And so the U that we want, you can think of this as like, this is our F1. This is our F2. This is our X1. This is our X2. And the X we want is 63 degrees Celsius. So F at a temperature of 63 degrees Celsius is approximated by F1, 2456 times 10 to the third, plus, and now we have the slope of this thing, so that is 2463.1 times 10 to the third minus 2456 times 10 to the third divided by x2 minus x1, so that's 65 minus 60. And then multiplied by x minus x1, so that's 63 minus 60. This should be, I left out the decimal here. It's not a super big deal, but 56.6.6. Okay. And what you get for your approximation is 2460.5 times 10 to the third joules per kilogram. Any questions about that? Okay, I'll give you a couple of problems like that to do, and that's it.
Are you going to want to see us show our work for this kind of thing? This seems like super ripe